Hey, it's Mr. Shrum, and we're going to look at reaction rates today. And I think this is our last physical science tutorial, and we're going to describe the reaction rates and identify factors that can affect how fast reactions happen. So, for an introduction, at some point today, you will undoubtedly eat carbs, unless you're on some weird keto diet. That's probably going to happen. Whether you eat breakfast cereal, oatmeal, if you like sandwiches, breads are carbs, spaghetti, noodles, fettuccine, all the good stuff. Your body uses the sugars that make up carbohydrates as fuel to keep your organ systems working properly. When you haven't eaten enough carbs, your body will let you know pretty quickly. People who cannot maintain normal blood sugar levels may suffer from diabetes. As carbs are broken down in your body, energy is released. This reaction happens slowly enough that the body can capture and use the energy released, but quickly enough to keep you alive and healthy. The body uses the following reaction to break down sugars in carbs and release energy. So here we have the equation. Let's see if we can balance that. So you have 6 and 6 atoms on the left-hand side here. And on the right-hand side, we have 6. We have just 1. So it needs some balancing. And what is your first instinct? Well, I would go with making sure the H's are doubled first. Here, let me work it out on my sheet of paper first, and then I'll show you guys. But we'll use these same methods we used last time. Six, and then we got CHO. Six, H got 12. 12. And then O, we have 6 plus 8. Over here we got 12 plus 6. Got 18. Six times 2. 6 plus 12 equals 18. Okay, sorry. Here, let me show you. Bam. Oh, it's not very big. Here, let me stop the sharing. All right, so here's the final product. That's a little messy. But you have this whole molecule here times 6 O2, and then you have 6 CO2 and 6 H2O. And if you add all of the atoms up on the left-hand side, now they equal those on the right-hand side, so we're good. But the first thing I did was multiply this one by 6 because there's 12 H's, so 6 times 2 equals 12 there. And then I multiplied this to make C equal to the left-hand side. So 6 there makes that 6 equals 6. And then since O2 is alone, you can adjust that last to make sure everything adds up. All right. So pro tip, wait to do the lone atom. Okay. Okay, cool. So let's get back to the intro. It's weird that they asked that. Oh my gosh. And there's the final equation. Now, this equation is known as cellular respiration, And it happens in almost every living thing on this planet. You may look at the reaction above and recognize it as a combustion reaction. Oxygen is a reactant, and carbon dioxide and water are products. And that is correct. But it's strange to think that a combustion reaction is happening in your body. We typically think of combustion reactions as being fires or explosions, but cellular respiration can be thought of as a very carefully controlled fire. The rate of the reaction is kept in check through a variety of controls. It's important to note that this reaction can be quite violent if it's not controlled. So, for example, grain elevators, such as the one here in this picture, are used to move grain up into storage facilities. Grains are really just clumps of carbs, which get refined and processed into breads and cereals. Surprisingly, grain elevators explode from time to time because those carbs ignite. In this lesson, we're going to look at why that reactions can take place at different rates and how those rates can be changed. So, if you're observing a chemical reaction, there are some hints that a reaction is taking place. If you see light, a different kind of color is being produced. You may hear the reaction make noise or feel heat radiating out from the reaction. These are called macroscopic properties because you can see them without a microscope. You can see them with your own human eye, and that makes it macro. On the smaller scale, or microscopic, details of a reaction can't be seen readily, so you need something to enhance your vision. Because you can't see what is going on with the particles in a chemical reaction, it's helpful to compare it to something that you can see. And we're going to imagine that a chemical reaction is like having a bunch of kids in a gymnasium. Some are wearing blue shirts, some are wearing red shirts, and all are wearing blindfolds. So let's say we have instructed the kids to walk around in the gym and to hold hands when they collide with someone else. Furthermore, only a red shirt and a blue shirt can react and end up holding hands. Blue shirts only hold hands with their right hand. Red shirts only hold hands with their left. In this analogy, we will consider the individual kids' reactants and the kids holding hands products. Finally, let's say that one of the rules is that a reactant can't react with a product because the product's hands are no longer available for a new connection or reaction. So imagine how that goes down. So there's at first only reactants or individuals that are not holding hands, but over time, people will find partners and they can pair up in products. Because they can't see, the reactants randomly wander around. Sometimes they run into other reactants, sometimes they collide with walls, and sometimes they don't run into anything for a pretty long time. And the reaction that has been described essentially outlines one of the basic principles of chemical reactions, and that is collision theory. And that theory states that for particles like atoms, compounds, and ions to react, they must collide with other particles. What isn't represented in our analogy is that the kinetic energy of the particles is important. If the reactants don't have enough kinetic energy or speed, they won't collide with enough force to cause a reaction. The kinetic energy of a reaction is really important. Essentially, energy needs to be invested into the reaction to get it going. This is called activation energy. Without it, most reactions won't happen at all. This can be a good thing, like grains in food, wood and paper. They are made up of a type of carb called cellulose, which is also made of sugars. If there weren't a need to overcome an activation energy threshold, the wooden desk that you may be sitting at would spontaneously catch fire. If there were not a need to overcome an activation energy threshold, the beach fire pit that you may be sitting around would spontaneously catch fire. Obviously, things don't spontaneously catch fire all the time, so that's good. Not only is the amount of kinetic energy in a reaction important, but the geometry of the reaction is a big factor as well. It would be hard for a kid in a red shirt and a kid in a blue shirt to react if they just happen to brush shoulders while walking about. The same is true for our reactants. They need to collide in such a way that a reaction is possible. So the figure to the left shows how the alignment of the reactant molecules results in a successful and an unsuccessful reaction. A, we have a successful reaction. B, not so much. So they just kind of collide, but they don't react. With enough kinetic energy and the correct geometry, the correct alignment, that provides the best case for a reaction to take place. Now that we understand a little bit about the collision theory, we're going to look at how we can measure the rate of a reaction. And the rate is really the speed of a reaction. So like a speed of a car, you can say that like that's a rate, a car rate. So think of that in terms of reactions. Really, we're just looking at how fast the reaction takes place. To describe the rate of a chemical reaction, we're going to use any unit of mass or any concentration over any unit of time. So grams per hour can work, moles per liter per second can count, and so on. Looking at the concentration of reactants and products over time, we would expect to see a relationship like the one shown in this graph. Initially, the concentration of reactant is high, but there is no product. Over time, the reactant is converted into product at the same rate that the product is being formed. The rate of this reaction could be measured in moles per liter per second. In this example, the reactant concentration decreases by 20 moles per liter every second. So the rate is 20 moles per second. Again, the important point about reaction rates is that it is a measure of how the amount of reactant or product changes over time. Clearly, the rate at which carbs react in the body is much slower than if they were to react in a grain elevator. We will be discussing how reaction rates can be changed throughout the rest of the lesson, so make sure that you keep this point in mind. Which of the following could be used to describe the rate of a reaction. So we need some type of mass or concentration divided by time. So that's the only one that is over a division of time. Now we have temperature and reaction rate. Before we explore how temperature and reaction rates are related, we're going to do a little experiment. And I'll show you the answers for these parts. Oh, well, you can make up your own hypothesis, make your own prediction, write it down for part A. Well, okay, maybe we're not going to do this activity, but I showed you the answers and they'll vary. Maybe I'll include a video of that in the Canvas page. From the reaction that was performed, we can safely conclude that the addition of heat increases the rate of a chemical reaction. Why do you think that's so? Well, if you add heat to a chemical reaction, the kinetic energy increases, and that means the speed of the particles moving increases as well. The temperature of the reaction increases. So the ultimate effect is that the rate of a reaction increases when heat is added. Which of the following correctly describes the effects of increasing temperature on the rate of a reaction? The rate increases and the time required for the reaction decreases because it's reacting faster. Concentration and reaction rate. So by giving reactants more room to run around in, we've essentially changed the concentration of our reactants. Concentration is a measure of the number of particles in a given space. So in chemistry, we typically deal with moles per liter because we increased the volume by moving to a larger space. And, oh, this is from last time. Chemistry mole we refer to mole as a unit of measurement for amount of substance. So you're saying 1 mole contains this many particles. So a mole is a unit, like the way an inch measures length, a mole measures the amount of something. So hopefully that does not confuse you. So if you have a lot of particles in a little space, that's really concentrated. But if you have a bigger space and the same amount of molecules, it'll be less concentrated. Think of like when you have soda with ice, and then after the ice melts, it kind of turns more watery. That means it's less concentrated. Okay, more particles means more collisions, which means a higher rate of reaction. So the more concentrated the reactants are, the more particles can collide. Therefore, the reaction rate goes up. If you decrease the volume, increase the concentration, the rate goes up. Drag each concentration to the chart to indicate the time and reaction rate required for that volume of concentration to react. So you have the reaction rate and the time and the concentration. Two. Oh. So all you really have to do is multiply this number by this number. So 0.1 times 10. Times 1, 10. Oh, whoops. And then 1,000 times 0.1. That leaves us with 100. So all you're doing is multiplying the reaction rate times time. That will give you the concentration. And to double check, yeah, the concentration divided by time, that should equal the reaction rate. Surface area and reaction rate. So how does the surface area affect the rate of a reaction? One of the easiest ways to increase the rate of a reaction is to increase the surface area. A familiar example is what you do when you eat. You chew your food, you swallow it, and then your stomach pulverizes the mixture even further. Chewing increases the surface area so you can finish digesting the food and absorb it as quickly as possible. Think of how this differs from boa constrictors, which ingest their food whole and then slowly digest it over a period of weeks. So when you eat every day, those guys take forever to digest their food. So how do you increase the surface area? Increasing the surface area to increase the reaction rate makes sense when you keep collision theory in mind. By having more particles available to react, there will be more collisions, which results in more product being formed. If the reactants are in the form of a lump, then only the particles on the outside of that lump can react. The particles inside the lump can't react with anything. So that explains why grain elevators sometimes explode. The grain dust that is produced when grain is moved around is made up of small particles containing carb molecules. Because there are many particles available to react with the oxygen in the air, it only takes a spark to set it off. Coal mines can be dangerous for the same reason that grain elevators are dangerous as well. While lumps of coal can initially be difficult to burn, coal dust is explosive. The high surface area makes it ideal for reacting with oxygen, especially in enclosed, limited volumes, such as coal mines or grain elevators. Mines and elevators for grain and coal, respectively, they have a need to have an efficient ventilation system. And the system of ventilation removes dust before it has a chance to ignite. So you need something that's constantly getting rid of those particles. Because the surface area of the reactant affects the rate of a reaction, the state of the reactant is also a factor. Most chemical reactions involve either solid, liquid, or gaseous reactants. And these states can affect the rate of a reaction. Solid reactants will react slowly. If at all, liquids will react more quickly, and gases even quicker still. So we're given 4 different reactions, and the state of each reactant is noted by the little subscript Sg or aqueous. Which has the highest rate of reaction? There are solid reactants present in the first 3 reactions. Despite the fact that there are also gaseous reactants in 2 of these reactions, these will still be slower than the final reaction, which involves 2 solutions. Which of the following reactions is slowest at room temperature? We're going to go with the solids. This reaction is slowest because its reactants have the least amount of surface area. Solids have the least amount of surface area, then liquids, and then gases have the most amount of surface area. And that brings us to the summary. Chemical reactions involve particles moving about and colliding. If they collide in just the right way and with the right amount of energy, a product can be formed. Various factors affect the rate at which product can be formed, but all of these factors can be traced back to collisions and energy. Keep these in mind as you go on, as these factors are important in most chemical reactions that you will discuss in this course. In this lesson, you have learned about, spelling error there, the collision theory of chemical reactions, how temperature affects the rate of a reaction. An increase in temperature increases the rate of a reaction, how concentration affects the rate of a reaction. If concentration goes up, so does the rate of a reaction. And an increase in surface area increases the rate of reaction as well. So if you increase temperature, concentration, and surface area, you will increase the reaction rate. And there is one other way to speed up the rate of a reaction, and that is with the use of a catalyst. Catalysts are remarkable in that they lower the activation energy necessary to start a chemical reaction. And they do this without participating in or being used up by the reaction. To use our gymnasium analogy one final time, adding a catalyst would be like having chaperones in the gym who help the reactants collide in a way that produces a reaction. So say you had kids that did not have blindfolds on, and they could help the blindfolded kids find another red shirt or blue shirt. Biological catalysts are called enzymes, and they are critical to keeping us alive. You will explore catalysts in more detail in another lesson, probably sometime, but this is the final one for this year. So far, we have discussed at length how to speed up reactions. What we haven't addressed in much detail is why you would want to. Are there situations where it is necessary to slow a reaction down? If so, how would you do this? How could you? Just keep these questions in mind in all types of science lessons. It's a good thing to ask, well, why do you want to use this information in the first place? But that's it for reaction rates. If you have any questions, let me know, and I will help you out as much as possible. But until next time, have a good one, and have a great rest of your day. Bye-bye.